usually measure angles using the degree system, right? A full circle is what? 360 degrees, right? But then when you think about where the number 360 comes from, it's a bit weird. Why not 100? Where does this 360 come from, right? If you say the full circle is 100, then instead of 90 degrees, you're going to have a quarter, 25 as the angle for the right angle, and so on and so on. You can very well think about another way to measure angles, right? And if you go back in history where all this started, you kind of realize that, oh, it was the ancient Sumerians who started with this 360 because they went by the 12 number system, right? So even now you count eggs by the dozen, right? Dozen is 12. Yeah. And then you start asking like, why 12? I mean, we have 10 fingers, so 10 seems like the most reasonable way to count. But Sumerians were using 12. So there's like some theory that cannot be verified, but they say, oh yeah, it's probably because Sumerians had like 6 fingers each, right? So they had like 12 fingers to count. That's why their number system was 12. Yeah. Then there's all these conspiracy theories like, oh, the Sumerians were aliens or something, and it's pretty convincing because Sumerians had so much advanced math that they already knew the Pythagorean theorem. They knew how to accurately figure out the days of the year. Calendar system was great, so they even predicted the end of the world, so they say. We don't know if it's true. Like,
2012?
Yeah. We passed that point, right? 2012 was the end of the world according to Sumerian calendar. We're still surviving, right?
Well, wasn't that
the Planet X and like pole shift and all these things? Yeah, it was kind of fun stuff. Yeah. Well, anyways, so there's this hypothetical theory about being 12, but I think the more convincing way of thinking is that, you know, when you report numbers, you count with your 10, but then you also have 2 feet, right? You can use your 2 feet. Why not toes, you might say, but then toes are harder to wiggle than fingers. So you have 10 fingers plus your feet, and you can use those to count. So that's probably it, yeah. And then they also thought about 5 as an important number, 5. So they also counted in the 60s. 5 times 12 is 60, and then 60 times 6 is 360. So that's why we ended up using 360 for the degree of a circle. And then, you know, the equilateral triangle is a pretty important geometrical object, and that seems to have 60 degrees. If you went by 100 degree system for the entire circle, then the 60 degree will be converted into some strange number, whereas in the 360 degree system, it has a whole number, 60 degrees as one corner of the equilateral triangle, so that it works nicely. So it's all good. So people have been used to 360 degrees. Everyone knows how to use it. 90 degrees is the right angle, the perpendicular angle. So people seem to be pretty happy, and we were happy for many, many years until calculus came along. Right? And when Newton developed calculus, and there were many advances in physics and math because of the calculus, at some point people pretty soon discovered that the degree system is ugly in the viewpoint of the calculus. And sadly, this course is not about calculus. This is pre-calculus course, and therefore you haven't seen anything calculus related yet. But just to give you a very vague idea of why this new kind of system is important, so they came up with this thing called Radian system of measuring angles, and it's just like meters and feet. Like people use centimeters and meters to measure length everywhere in the world, but then somehow in America we use inches, and it's kind of backwards. It's we don't like science, so we. I guess people from other countries always have the problem, like thinking in terms of meters, no, in terms of inches and feet. It's hard, right? Is that right? Yeah. Some of my foreign students might think that way. Yeah, I had the same problem. But anyways, radians is just another way of measuring angles, a new unit. And just to give you my point of why this is more convenient, is that most of you are going to take calculus, right? In calculus, there's something called a derivative. So for example, x squared differentiates to 2x. You may have heard of this. How many of you know this? Some?
Yeah.
Okay, well, but then if you have sine of x, you get cosine of x, provided that this x is measured in radians. Now, some of you not even have seen sine and cosine. It's just some kind of function. Okay? So sine derivative is cosine. On the other hand, if you had sine of x degrees, then you get some crazy number in front. You get pi over 180 in front, and then cosine of x degrees. So when you use degrees, calculating in calculus gives you these ugly numbers in front, and it screws up all kinds of things. So that's why when physicists and mathematicians started calculating things that have degrees in there, they realized, okay, degrees are ugly. We should use this new system, which is called the radians. Right? Now, even at the level of everyday math, the radian system, you'll see that it has some advantages. But in most cases, if you're working for everyday math, like trying to build a house or design something, you usually want to measure angles in degrees, not radians. Okay, so that's confusing. Okay. All right. So what is it? What is radians? So let's start talking about what radians actually is. So radians is tied to this unit circle. So I have to first explain what a unit circle is, because to define radians you need a unit circle. A unit circle is a circle of radius 1. Unit circle is a circle of radius 1. And especially when you talk about circles on the plane, the real plane, in the xy plane, then it's the specific one that's centered at the origin. Okay? That's called the unit circle. Now, using the unit circle, definition of the radians goes like this. Suppose somebody gives you some angle, any angle, okay? And he says, here you go, measure this, okay? And the way you're going to measure it by this thing called radians is going to be, you move this over here so that it copies over as this angle here. Then, on the unit circle, that is going to give you an arc of the unit circle, right? And this length right here, this length, will be called the radian measure of the angle. That's what radian is. Okay? Now, think about it. If your angle is small, what happens to this arc length? It becomes small, right? If your angle is big, the arc length is also big. So this arc length does track whether your angle is small or big, right? It just gives you a different quantity. Right? Okay. Now, to better understand what that is doing, you really need to know the circumference of the unit circle. So let's think about that, circumference of the unit circle. Here's a unit circle, and the question is, what is the circumference? What's this length around? And to refresh you with the basic knowledge of geometry, let me draw this one. Here's a diameter one circle. So this is a radius one circle, but this is diameter one circle. If the diameter is 1, what's the circumference?
3.14.
Yeah, which is the pi, right?
Yeah.
So this length over here is what we know as the pi, which is about 3.14, right? Or 16, 3.1416. And this pi has a long history. Like, if you ever read the Bible or the Quran, you will see some places where it says, it talks about a circular column for buildings, and then it says that the circumference of the column should be 3 times the diameter. Where is the 3 coming from? It's there that at that ancient times, people approximately thought about 3.1416 as about 3 times the diameter. That's what they knew. I mean, you draw a circle and you start measuring around, and you get about 3 times the diameter, right? Okay. So that's what pi is, right? But then look, this is double this size, right? So what do you think the circumference of this one is?
2 pi.
2 pi, right? So this one will have the circumference equals to 2 pi. Now, what does that mean for our radius? Here's what it means. If you have 360 degrees as an angle, and you put it on the unit circle and measure the circumference, or the length, you get what? On the unit circle, what is this length again?
2 pi.
2 pi. So you get that 2 pi radius. You get that 2 pi radius is same thing as 360 degrees. So here's the radian measure, and this is the degree measure of angles. Just like there are 2 different ways of measuring lengths, inches and centimeters, there's also 2 different ways of measuring angles, degrees and radians. Okay, now once we have this, we will also take this thing and divide both sides by 2. And that gives you pi radians equals 180 degrees. And I'm going to put a box around it because that is going to be something that you use over and over and over again. Okay? So pi radians equals 180 degrees is more fundamental than this one, although this kind of has a picture. Actually, this one also has a picture, and it's instructive to remember this picture. The picture goes like this. If you have a half circle of radius 1, right? What is this length? What's the length of the half circle?
Pi.
Pi. Why? Because the entire thing is 2 pi, and you have half of it, right? So this length is pi. This length.
Is it pi or is it pi radian?
I'm saying that the length gives you the radian measure, right? So because this length is pi, I know that this angle that we talk about will be the pi radians, right?
Okay.
So this angle will be pi radians. But what is that? That's exactly 180 degrees, isn't it? 180 degrees gives you this. So just think about this picture. If you know that this length is pi, then you know this already. Okay? And we are better at remembering pictures than words. So this is something that you should be putting in your mind. Okay? So half circle, that's pi. Done. Okay?
Half circle when it has a radius of 1.
Yeah. Half circle with radius 1 will give you pi. Yeah. All right. So now we're ready to solve some questions. Example 1. let's think about the following question. Convert 60 degrees to radians. Okay, 60 degrees that we know very well. Okay.
Pi over 3.
Hmm?
Is it pi over 3?
That's very good. Yeah. So solution. You know that pi radians is 180 degrees, right? But then 180 divided by what gives you 60? 180 divided by what gives you 60?
3.
Huh? 3, right? So you can divide both sides by 3. And now what do you get? You get pi over 3 radians equals to 60 degrees. Done. Seems very simple, right? Now, that, however, makes you more nervous because I'm not giving you a formula. I'm just telling you what to do, but then how would you know to take that and divide by 3? What if it doesn't work out, right? So now I owe you a second solution to this, which would involve a formula. So let me show you this by using formula. Solution 2. So here's what you do. 60 degrees is same as 60 degrees times pi radians over 180 degrees. Okay, why is that? Well, let's think about this. See, pi radians is the same as 180 degrees. They're the same. So, if I take this and divide both sides by 180 degrees, what do you get on the right side? What do you get on the right side if I divide both sides by 180 degrees? Should I write it? 180 degrees divided by 180 degrees. What do you get?
1.
1. You get 1. Right? This is just 1. So pi radians over 180 degrees is just 1. This value is 1. And anything is same as 8 times 1. You would agree with this, right? So this is same thing as 60 times pi radians over 180 degrees, because that's just 1. Okay.
So what's the formula?
The formula is that whenever you want to convert from degree to radians, you just multiply pi radians over 180 degrees. I'll write that out so that you can organize it better. But right now I'm just showing you the reasoning, the rationale behind why it works that way. Okay? And now degree cancels. Okay? And when you multiply a number to a fraction, it only multiplies to the top. So you have 60 pi 180 radians. Okay? But then you can cancel the zeros out. 6 and 18, they are both divisible by 6. So let's divide top and bottom by 6. What do you get? You get pi over 18 divided by 6 is 3. Which gives you the exact same answer as the previous one. Do you agree? Right. Now the thing that is a bit perplexing is pi radians over 180 degrees, while this is equal to 1, pi over 180 is not equal to 1. This will be ridiculous, right? Here's what I'm trying to say. See, 1 inch is same as 2.54 centimeters. Okay? So, if you have 1 inch divided by 2.54 centimeters, that's equal to 1. Because these two are the same length. Now, is it still true if you do 1 divided by 2.54 is equal to 1? No way. If you drop the units, it's no longer true. Yeah, You need to have the units for this to work out. Okay? In other words, units themselves have meaning. If you drop it, it's no longer true. Okay? 1 over 2.54 is something like, what is that? If you multiply 4 top and bottom, it's 0.4. This is about 0.4. Pi over 180, pi is about 3, so it's 1 over 60. That's like what, 0.03 or something like that, yeah. No, 0. I don't know, yeah, so some very small value. It's very far from 1, okay? So when I said pi radians over 180 degrees is 1, some of you may be confused because like pi is like 3 and 180 is so big, how can that be 1? But I'm not saying that. I'm saying that pi radians over 180 degrees is 1. It's not true that pi over 180 is 1, okay? You get that? Okay. So that was the fine point. But once you accept that, here's a way to go from degrees to radians. So degrees, if you want to go from degrees to radians, you multiply it by pi radians over 180 degrees. And this works because, as you can see, if you multiply radians over degrees, degrees cancel, and you end up with something that's radians. Is that okay? Yeah. Yeah. So that should be obvious. Now, what if you want to go the other way? If you want to go from radians to degrees, then you would be multiplying 180 degrees over, tell me, 180 degrees over? Make a guess. Pi radians. Because again, this over this is 1, right? Multiplication by 1 doesn't change anything, but it does change the unit. If you multiply this, the radians will cancel away and you will end up with a degree. Okay? So let me give you that second example. Okay, so the second example would be convert 7 pi over 12 to degrees. Okay. Solution. We just go by this, right? So how do you do it? 7 pi over 12 radians. By the way, often, I'm not going to write radians because radians is considered as more fundamental. It's more natural because the math forces itself. Okay, so once math advances to the calculus level, it kind of suggests a natural unit for measuring angles, which is the radians. So radians has the more natural feeling, so often I'll say 7 pi over 12 is the angle, but when I write this, that I might not say radians, but it means it's the radian angle, okay? All right, so 7 pi over 12 radians to degrees. How do you convert that? Well, here it is. 7 pi over 12 radians is equal to 7 pi radians over 12 times this thing, 180 degrees over pi radians. And you can see that the radians cancel away. Pi and pi also cancels away. And now you have 7 times 180 over 12 degrees. Okay, the entire thing degrees. And then now let's divide top and bottom by 6, because that makes things easier. Okay. So 6 times 3 is 18, so it would be 30 degrees. 7 times 30. 12 divided by 6 would be 2. And then 7 times 30 is 210 degrees. Divided by 2 will give you 105 degrees. Okay? So that's how you do it. But then let me show you a second method which is quicker. I like this better, but the second method only applies if your radian measure has a pi. So if angle contains pi, okay, you can use this method if it has a pi. And the way you do it is, see, you have 7 pi over 12 radians. You look at this and say, what is pi radians again? 180 degrees, right? So you rewrite this as 7 times 180 degrees over 12, and now everything else follows, right? You divide top and bottom by 6, so it's 7 times 30 degrees over 2, and 7 times 30 is 210 degrees, divided by 2, half of 210 degrees is 105. Done. So you get the result much quicker if you can just convert the pi radians to 180 degrees. That's a better method. But you still want to use this because sometimes your angle might not have pi in there. So here's example 3. Convert 1 radians to degrees. So let's think about this. 1 radians to degrees. So we just use radians to degrees. So solution, 1 radians is equal to 1 radians times 180 degrees over pi radians. Radians cancel, and you end up with 180 divided by pi degrees. Right? So it gives you an ugly number. And just out of curiosity, if we do 180 divided by pi, you end up with this being about 57.296 degrees. Okay. So it's close to 60 degrees. Of course, pi is about 3, so it's close to 60 degrees. And the idea is this. This 1 radian, if you drew the picture for it, it's like you have this 1 radians is something like a 60 degree, but slightly shorter than 60 degrees. Okay? So it's about 57 degrees. 1 radians is about 57 degrees. Okay. So that's why you probably need to know this formula. But I really don't like this picture because it kind of gives you the wrong idea that radians are hard. It's like 1 radian gives you some ugly number, so it looks hard. But it shouldn't be. So rather than this, you should always stick to pi radians being same as 180 degrees. That should be just repeated over and over again, along with that picture. Okay. So yeah. So sometimes you have no choice but to use this formula, but in many cases, what you will be able to do is to just convert pi radians as 180 degrees, and you can convert from radians to degrees. Okay. For part A, I'm pretty sure you just multiply by pi over 180 to get the
Pi over 9.
huh?
Not pi over 9.
No, that's not right.
That's not right?
That's not right.
You serious?
Yeah, I'm serious.
No.
Why would I be joking about?
I don't know.
Okay, so 150 degrees, you would do this by, well, you can multiply by pi over 180, but let me show you a different method. So think about 150 as 5 times 30 degrees. Now, 30, 45, 60, 90, these are called special angles, and those will be something that we prefer because they happen to be some integer. If you take pi 180 degrees and divide by 2, 3, 4, and 6, you get those values. Okay, so those are preferred. Okay, so we can say 150 degrees is 5 times 30 degrees, and say 30 degrees is 180 degrees divided by what? 18 divided by what is 3? 6, right? It's like this. But then what is 180 degrees?
Pi rad.
Pi, right? It's pi radians. So you end up with 5 pi over 6 radians. And you would have gotten the same answer if you multiplied by pi over 180. You got the same thing? Okay,
Yeah.
good. So I'm just giving you a different method. Here, it has a pi, so the easier way would be just replace pi radians by 180 degrees. And now you have 180 divided by 6. What's that? 30. So 11 times 30 degrees. What's that? 330 degrees. Okay? And then 4.5 radians. This, it doesn't have a pi, so you have no choice but to multiply by 180 degrees over pi radians. Okay. So there's a radians here, we'll cancel those out. And therefore you get 4.5 times 180 divided by pi degrees.
810 over pi.
What?
810 over pi.
No, that's too large.
180 times
4.5 times 180 divided by pi gives you 257.83 degrees. Okay. That's about ballpark.
No, I did it wrong. You were right.
Okay. Now, one thing that you should keep in mind.
Same thing.
Huh?
No, it's just I left it over pi instead of.
Oh, I see. You just multiply the
Yeah.
top and okay. Yeah, I meant to
Okay.
do the whole thing. All right. So this should be about right because what is 360 degrees in radians? 360 degrees in radians is
2 pi right.
2 pi. Right? 2 pi. 2 pi is 360 degrees, but pi is about 3. So about 6 radians gives you the full circle. Do you agree? 6 radians will be slightly less than a full circle because actually 6.28 something will be the full circle. Right? So you have 6 as the full circle, but then you have something short of 6, right? But it's definitely bigger than 3. Right? 3 is like the pi, 180 degrees. So this should be something between 180 degrees to 360 degrees. And indeed, your value comes out to be 257.83. So that's about right. Okay. It's good to have that kind of checks so that if you make a mistake, you'll realize it. Okay. All right, so let me save this result because I want to use this. Let's start off with a question. What is the arc length? And here's a picture. Here's 150 degrees. And then you have this radius as 4. And then this length here, we're going to call this length as S, okay? So the question is, what is this S? Suppose you're given a circle of radius 4, and you create an arc of central angle 150 degrees. What is the arc length? That's the question. Now let me give you 2 solutions. Solution 1 Well, what is the entire arc length? Well, the formula for the circumference of the circle is 2 pi r, where r is the radius, okay? It's really diameter times pi, because twice of the radius is the diameter, right? So if you do diameter times pi, you end up with the circumference of the circle. So in our case, the circumference of the circle will be what? 2 times pi times radius?
4.
4. So what is that same as?
8 pi.
8 pi. So you get 8 pi. But that's the entire thing. Now you have to think about the proportion that this part of the arc gives you. Okay? And the proportion is S would be 8 pi times 150 degrees out of the full 360 degrees. Right? That will give you the proportion that this arc would have with respect to the entire circle. Right? And then, since degrees cancel and zeros cancel, and both top and bottom can be divided by 3, this is 8 pi times 5 over 12, because 3 times 5 is 15, and 3 times 12 is 36. So after dividing top and bottom by 3, this is what you get. And then when you multiply a number to a fraction, it only multiplies to the top. So 5 times 8 is 40 pi over 12. And then furthermore, I see that both top and bottom can be divided by 4. Right? So if I divide top and bottom by 4, it's 10 pi over 3. So that's the arc length. So for example, if this is in inches, 4 inches, then the arc length will be 10 pi over 3 inches. Okay.
You just use a calculator to find the answer, get to that point.
I might ask you to give me exact values, so this should be the answer.
Okay.
Okay, now let me give you a second solution. This first solution might make you a little nervous because it's more geometric. I'm not presenting you with any formula. So let me give you a formula. It might look easier then. Okay? So the way you get the formula is by thinking of the following circle. Think about the central unit circle for inside that radius 4 circle. Okay? Then here's a question. What is this length cut out by 150 degrees for the unit circle? Well, we know that that was how you measure angles in radians, right? And we actually solved that question. 150 degrees is 5 pi over 6 radians in radian measure, right? So this length right here is really 5 pi over 6 radians. Okay? That's what this length is. Because radian is same as the arc length for the unit circle. Then, think about this. What would the ratio between the small one to the big one be? Well, this is 1, that's 4. So what do?
Multiplied by 4.
You just multiply by 4 and that's the answer. So the second solution does this. To get the arc length, all you have to do is measure the theta in radian mode. It has to be in radians. If it's in degrees, you can't use this, okay? So that's why this is important. And then multiply by the radius that you're given, which in our case is 4. That's the radius, right? Because if this radius is given, you just multiply that much to make this arc bigger, to fit into the bigger circle of radius r. That's what you're doing. So you just have to take the arc 150 degrees in radian mode, 5 pi over 6, and you multiply this by 4. And now let's see, 6 and 4, that's 2 and 3. 2 times 5 is 10 pi over 3. So it's done. Very simple, right? So we just learned this nice formula. Arc length equals to theta times r. Now this theta is a Greek letter. It's a Greek alphabet that has a sound of th. But when you try to remember this formula, it's easier to just read this as if this was an alphabet O. So you can just read this as SOR. SOR. That's easy, right? It's easy to remember, right? So can you repeat after me? SOR.
SOR.
SOR. Right?
SOR.
SOR. What's the formula for? It's the formula for the arc length when your central angle is given as theta and the radius is given as r. Okay? So now let me give you a slightly challenging question using the arc length formula. Okay, question. Do you know what RPM means? Rotations per minute. That's how you, or revolutions per minute, right? Yeah. That's how you measure the power of an engine, right? When you are driving a car, in your front panel, there's the RPM value. Sometimes it goes like very high, like 1,000, 2,000, something like that. That RPM is different from the wheels of rotations per minute. And this one is rather slow because it's saying that it takes more than 1 second to do a full revolution. But anyways, if that's given, it's asking us to know how far this wheel traveled. Right? So let's try to solve this one using the SOR formula. Okay, solution. So after 10 minutes, how many revolutions have you done? How many rotations have you completed? Each minute you have 40 revolutions, right? So 10 minutes what?
400.
400 revolutions, right? That's what you have. And now you have to think about what one revolution is in terms of radians. One full rotation is same as what radians? One full rotation. 2 pi. 360 degrees is 2 pi, right? So now you say that the angle that you've rotated, right, is same as 400 times 2 pi, which is equal to 800 pi. Right? And now you want to know how far the arc length traveled, because this rotation really gives you the linear distance that the wheel traveled, right? So we just have to calculate using, what's the formula again? SOR. Right? SOR. So you say S is now equals to 800 pi is your central angle. What's the radius? 5. So let's use the calculator for this as well. 5 times 8 is 40, so 4,000 pi is what you get. So 4,000 times pi gives you approximately 12,566 feet. That's how far you've traveled. Okay? So it's pretty neat. Using radians allows you to have a simple formula for arc length. If you use degrees, then that formula will look harder. Okay? So you can still justify without the calculus that radians have a place in everyday math. But you know, still, if we weren't using calculus that much, radians would never be popular. It's just that because of calculus, we use radians. Okay. So now let's talk about area of the sector. This time, let me give you another question of the same picture, but with slightly different goals. So again, this is 150 degrees, radius 4. But now the question is, what is this area? And the way you calculate the area geometrically is still basically the same idea. You calculate the area of the entire circle, and you just have to figure out what's the proportion for it. Okay? So let's see. What's the formula for the area of a circle?
Pi r squared.
Pi r squared. Okay? So let's remember that. Okay? So the circumference is 2 pi r. Area is pi r squared. These two appear enough times that you should memorize those separately. And in our case, what is it? This is pi times 4 squared, which is 16. So it's 16 pi. And then the area of a sector that we have, the area in question will be, it's not the entire circle, but only 150 degrees out of 360 degrees. Right? Now, I think some of you still have trouble realizing that, so think about the picture like this. Suppose this is a gigantic pizza, and you order the pizza, and it came in 12 slices. Right? So it's like you have 12 slices, and you have 150 degrees would be like 5 slices. Have you ever looked at pizza slices and thought about these central angles and stuff like that?
No.
You did? Okay.
Yes, you.
Yeah, I do. Yeah. Sometimes I look at the slice of a pizza and I think, okay, what is the angle? All right. Anyways, so this is like 5 slices of pizza if you divided the pizza into 12 equal parts, okay? Yeah. Because 360 divided by 12 is 30 degrees. So you have 30, 30, 30, 30, 30. 30 times 5 gives you 150 degrees. Okay? But then, think about the following. The full pizza is 12 slices. And out of that, let's say you're eating 5 slices of that. Okay? So what do you do? It's 5 slices out of the 12. Isn't that what we're doing? Right? And then 16 and 12, they both have 4 as a common factor. So if you divide by 4, this will be 4 and this will be 3. 4 times 5 is 20, so you have 20 pi over 3 as the area. So if this was 4 inches, then this would be 20 pi over 3 inches. Okay? So that's my first solution, but of course, we need a formula. That one is just using geometry.
Wait, so
Yeah.
is the formula area equals pi r squared?
No, that's the formula for the entire circle. I want the area of a sector,
Okay.
which is like this.
Okay,
Right?
got it.
Yeah. I mean, this one was simple enough for geometric purposes. In a geometric viewpoint, it was simple enough. But what if it's some angle that you can't really try to figure out? So you need a formula. So let's try to work on the formula. Okay. So if we work on the formula, here's what happens. You can think of that formula right there as the following. You can think of it as 16 pi times 150 degrees over 180 degrees, right? No, over 360 degrees. And this, if you simplify it, does give you 5 slices out of 12 slices, right? So that's what we did to solve it. Now I want to kind of change this formula so that it looks like a formula. So instead of 16 pi, let's remember that this really came from pi r squared, right? Is that right? Okay. And then just think of 150 degrees. Earlier on, we showed that 150 degrees is the same as 5 pi over 6. So replace 150 degrees as 5 pi over 6 radians. Okay. And then, what is 360 in radians? Come on, I asked you.
2 pi rad.
2 pi radians, right? So it's 2 pi. So you can rewrite this as in terms of ratio between radians, and I like this because then I can instead divide these 2 pi's out and think of pi over 2 pi as just 1/2. You can write like this. Okay, so because pi over 2 pi is 1/2, and you have r squared, and 5 pi over 6 is here. And then just remember that 5 pi over 6 was our angle, central angle, in radians format, right? And now, here's our result. This is the formula for the sector, 1/2 r squared times theta. But for this formula to work, you have to make sure that your theta is in radians, because we use radians to make pi over 2 pi as a simple number, 1/2. Okay? But even that is too complicated, so we're going to change that a little bit more and rewrite this as 1/2 times theta times r, because r times r is r squared, and you still have a theta, right? I like this because I know what theta r is. What is theta r equal to?
Theta r squared? Oh.
No, theta times r is same as? Theta r is same as? S. SOR, right?
Okay.
So I can rewrite this as 1/2 SR. And that's the formula for the area of a sector. So using all this, let me show you the second method. Solution 2 of the same problem. Okay, so this is like solution 1. Okay, the formula says I first have to calculate S. What is S? S is SOR, right? And our central angle in terms of radians is 5 pi over 6. And my radius R is 4. That's in the problem, right? And then you write down, well, we can simplify this. So these are both even. So this is 3 and that's 2. So it's 10 pi over 3. And then the next calculation we do is area would be 1/2 times S times R, where S is 10 pi over 3, and R is 4, but 4 divided by 2 is just 2. So what's our final answer?
20 pi over 3.
20 pi over 3. You get the same exact answer because we kind of reverse engineered the first answer to get at this formula here. So that's my demonstration of the formula, but wait. I have just one more comment to make about this formula. Take this red sector, rotate this around so that it looks like this. Okay, you have this sector. Now, if you draw a straight line down here, what is this length? No. This angle is 150 degrees. That's still true. I'm asking you what this length is.
4.
4, because it's the radius. This is 4, that's 4, that's 4. It's a part of a circle. Radius of a circle is always the same, right? Okay? And then, what is this length? That's our length S, right? So, if I go by a more generic situation, here's what we have. This length will be R. This is S. And what am I saying? I'm claiming that this area is same as 1/2 base times height. Oh, that's the formula for the triangle. But it's not a triangle, it's a sector. It looks like a triangle, but it's not really a triangle, right? So it's kind of amazing coincidence that the formula itself resembles the formula for the area of a triangle. And the way it works is this. If you had a radius r and arc length s, you can flatten this out to make another triangle like that, so that this is also S, and this triangle will have the same area as the given sector. Okay. That's what this coincidence is saying. So it's kind of strange that that's true, but that's what we just see. Okay. All right, that's all for today.